Poisson's ratio formulas. So, Poisson's ratio equals the negative lateral strain divided by the axial strain. This is the ratio of transverse contraction strain to longitudinal extension strain in the direction of the stretching force. Tensile deformation is considered positive, and compressive deformation is considered negative. The definition of Poisson's ratio contains a minus sign so that the normal materials have a positive ratio. Again, here's the formula. And don't forget the negative, because as the axial increases, as it gets pulled away from center line, the lateral coming down decreases, so you have a negative number. And remember that the axial strain equals the change in length divided by the length. The lateral strain is the negative change in length, how much smaller it gets, divided by the lateral length. So you find the two strain values and insert them into the formula. The lateral strain equals the axial strain times negative Poisson's ratio. Okay, so what is the deformation in X and Z when a piece of magnesium is 25 inches long and has a 0.75 by 500 rectangle end and stretches 0.5? First, we find the axial strain. So the axial deformation divided by the original length. So I said that it stretched 0.5 of an inch, so we'll take the strain, the change in length divided by the length, and we say 0.5 divided by 0.25, and that equals 0.020. So we found the strain. And then we use Poisson's ratio to find the lateral strain. The lateral strain, y and x, equals the axial strain times the negative Poisson's ratio. So I'll take 20 thousandths and use the Poisson's ratio of negative 0.35. So 0.020 times negative 0.35 equals negative 0.007, which is the lateral strain. Now we use the lateral strain to find the lateral deformation in y and z. So lateral deformation in y is the lateral strain times the original length. So we got a negative 0.007 times 0.75. That lateral deformation in y is negative 0.00525. Or we can round it to negative 0.005 or negative 5 thousandths. So the lateral deformation in z, which is the lateral strain times the original length. So the lateral deformation equals negative 0.007 again, and just times the 500 thousandths. And the lateral deformation is negative 0.0035. So if we check Poisson's ratio, the negative lateral strain divided by the axial strain, Poisson's ratio equals negative, and then in parentheses, negative 0.007 divided by 20 thousandths, 0.020, which equals, we have double negative, so that's a positive number, and that's 0.35. And then we look up magnesium, and we find that 0.35 is indeed Poisson's ratio for magnesium. It sounds a little complicated, but if you work it step by step, you'll get the right answer. Okay, let's start talking about the chemical properties of different materials. So corrosion resistance. Corrosion resistance is probably the most important chemical property of a metal. Materials are used in different environments, and they're exposed to many different chemicals such as oxygen, chlorine, water, oils. The reaction of the material to an environment is called corrosion. Common types of corrosion. Some you've seen quite often. Oxidation, the reaction of a material exposed to air. Example, iron and iron-rich steels oxide to form rust. Galvanic corrosion, also called bimetallic corrosion, is an electrochemical process in which one metal corrodes preferentially when it is in electrical contact with another in the presence of an electrolyte. Electrochemical corrosion, corrosion that occurs when electrical currents set up on materials in a liquid or moist environment. You've seen this. The most common is battery corrosion. Some plastics are destroyed by sunlight and oxygen. Rubber oxidation is a result of aging. As it ages, it loses its elasticity. Water absorption, the tendency of polymers and ceramics to absorb water. It increases the material's weight and volume and causes them to warp and swell. Chemical properties continued. Pitting, inconsistencies within the molecular and the atomic compositions of the materials, such as residual stress, cracks, and etc. Environments can exacerbate the process, such as salt water or chlorine bleach. Intergranular corrosion, caused by improper heat treating or improper chemical compositions. Stress corrosion cracking, caused by improper processing, and this is very common. Electrical properties. Highly conductive materials allow electricity to flow freely through it. Dielectric strength allows high voltages over a long period of time without significant damage to the material. Magnetic properties. Magnetic susceptibility is a material's ability to be magnetized. Ferrous metals are magnetic. Most non-ferrous metals are not. Ferrous metals at high temperatures lose their magnetic properties, and we'll talk about this as we go through steels and upper transformation temperatures and the unique properties of metals as we raise the temperatures in the materials while we're processing them. Thermal properties. Strength, hardness, ductility, modulus of elasticity are affected by the temperature changes. Some metals' characteristics are affected more than others. When a metal is heated, it expands. When it's cooled, it contracts. The amount of expansion from heat is determined by the coefficient of thermal expansion, and each different type of material has a different level of coefficient. Talk a little bit more about that here. Coefficient of thermal expansion describes how fast the material expands when subjected to heat. The formula is the change in length equals A times L times change in temperature. Okay? A is the coefficient of thermal expansion. That's change in length. L equals original length and change in temperature. Okay, so let's do an example, a real life example of how thermal expansion can affect a fixture that we're using. Okay, so we know that alpha, the A, is the coefficient of thermal expansion. And so we'll have to look that up. The material is aluminum, so we look on our chart, and aluminum is 12.8 times 10 to the negative 6. So what we're looking for is the change in length. So we have a fixture, an aluminum part, that is 10 inches by 2 inches by 125 thick, and the pins on the fixture are exactly 8 inches apart. Okay? The holes on the part are 1/1000ths larger than the pins. Okay, so that means we have 1/1000th on each pin that we could move over and it would still fit. Okay? So at 70 degrees, the part fits on the fixture. Will it still fit if the part is raised to a temperature of 100 degrees? So what we're looking for is we're trying to find out how far apart that's going to spread when we heat up that part. So what do we know? We know that we know A, which is alpha, the Greek A, alpha, is the coefficient, 12.8 times 10 to the negative 6. We know the length, which is how far apart they are. They're 8 inches apart. We know the change in temperature. So it's 100 minus 70, so that's 30 degrees change of temperature. So we throw all that into a formula. So first thing we would do is throw in the coefficient, 12.8 times 10 to the negative 6 times the 8-inch distance times 30. Okay, 30 is the change in temperature. So if we work that equation out, the change in length should be just a slight amount over 3 thousandths. If we round it, it should be 0.003. Now, will the part fit? I don't think so. We only have a thousandths. So even if we had a thousandths on each one and we called it 2 thousandths clearance, it moved 3 thousandths. So that part will no longer fit on that fixture. If we raise the temperature in the shop gets to 100 degrees. Does that make sense? Throw these numbers in your formula, double check yourself. Materials melting points. Figure 425 provides a sample of materials melting points. The temperature at which a material changes from a solid to a liquid state. If heat travels quickly through a material, it is said to have high thermal conductivity. Aluminum and copper are examples of metals with high thermal conductivity. Heat capacity is the amount of heat needed to raise a material's temperature by 1 degree. Weight and density. The ratio of the weight of a material to its volume is referred to as its density. In this text, we will use weight and density interchangeably. They'll be the same thing for us, okay? Lightweight metals are important in engineering and aerospace applications. Aluminum, magnesium, titanium are examples of lightweight metals. Lead, carbide, nickel, chromium, cadmium are examples of heavy metals. Some of these heavy metals are toxic and can cause cancer and blood disorders from exposure. You got to be careful. Beryllium copper is safe to machine, but if you grind it or put it on a sander, the dust is carcinogenic. Figure 428 shows the density of common metals in pounds per cubic foot. Wear, machinability, and weldability. These are things that are important to the machinist and the welder. Wear is the ability of a material to withstand prolonged exposure to frictional forces. Machinability is the ease of which a material can be cut. Aluminum and magnesium have good machinability, where titanium and Inconel is an alloy steel, are difficult to machine. Weldability is just that. It's the ease in which a material can be fabricated using any of the various welding techniques, arc, MIG, TIG, gas. And look at the examples of Figure 429 and Figure 430. Now, this brings us to the end of Chapter 4. Chapter 4 is kind of a bear. You're going to have the most math, and it's one of the longest chapters we're going to have to do. You won't see a ton of these formulas after this from here on out. You may have to go back and use them, so make sure you know how to work each formula and remember where they're at. Okay, thank you very much.